Welcome to the 6th session on ionic equilibrium. In this session, we will be dealing with the dissociation constants of acids and bases, especially weak acids and weak bases. Now, let us see what do you mean by a dissociation constant. Dissociation constant is a value which gives us the measure like how strong an acid or a base is. That is why we go for dissociation constants. If the dissociation constant values are high, we know that the acid is perfectly ionized and that will be a strong acid. If it is very low, it shows that it is a very weak acid and the ionization is very feeble. Now, let us go for that. Ionization constants of weak acids and pKa. The ionization constant is represented as Ka, and pKa, as I have told you before, it is the negative logarithm of the value of Ka. Okay. Let Ha is taken as a weak acid and this Ha dissociates into H3O plus, that is in the presence of water, to H3O plus and A minus as the anion. Okay. Now, let us consider the concentrations. Initially, if I am starting with C moles of Ha per liter, initially it does not get dissociated and therefore, the concentration of H3O plus and A minus are 0 moles. At equilibrium, when I consider the dissociation constant or ionization constant as alpha, that to be for 1 mole, and therefore, for C moles it will be C into 1 minus alpha. For 1 mole, the remaining undissociated will be 1 minus alpha, and for C moles it is C multiplied by 1 minus alpha. In the case of H3O, as we know that if I am starting with 1 mole of Ha, I will get 1 mole of H3O plus and 1 mole of A minus. So, if I am starting with C moles and alpha is the degree of ionization, H3O plus formed will be C alpha and A minus is also C alpha. Next, what I am going to do is, I am going to write an equilibrium constant for this, that is Ka of the acid, to show that it is an equilibrium constant for dissociation of an acid. Ka is equal to concentration of H3O plus into concentration of A minus whole divided by concentration of Ha. Now, why do you take only Ha but not water? Because water is taken in excess and concentration of water is considered to be constant, and therefore, Ka is given by the expression H3O plus into concentration of A minus divided by concentration of Ha. Now, at equilibrium we know that the concentrations are given by C into alpha for H3O plus into A minus, the concentration is C into alpha whole divided by the concentration of Ha is equal to C into 1 minus alpha. Now, cancelling the terms, the expression takes the form Ka is equal to C into alpha square whole divided by 1 minus alpha. This is the accurate value for dissociation constant of an acid. Now, we are going for an approximation. Since it is a weak acid, ionizes feebly, or you can say that very little, and therefore, 1 minus alpha, because alpha will be very small and 1 minus alpha can be approximated to 1 itself. Now, here the value of Ka is equal to then C alpha square, because this becomes 1, or alpha will be equal to square root of Ka by C. Now, Ka is the ionization constant, and if I take negative logarithm minus of log Ka can be taken as Pka. Now, let us go for the explanation. What happens when concentration increases? When concentration increases, alpha decreases, which means that at higher concentrations the dissociation is very little, and if concentration decreases, that is in dilute solution, the ionization is highly increased. Next, how will we compare the relative strength of weak acids? Like we know that we have two acids, acid 1 and acid 2. Let alpha 1 be the ionization degree of ionization for acid 1 and that be for alpha 2 for the second one. We know that alpha is equal to square root of Ka by C. For an acid, it is square root of Ka by C, where Ka is the ionization constant of an acid. Now, if I am putting it as alpha 1, I will give the subscript 1 for the first one, and therefore, this can be written as alpha 1 is equal to square root of Ka 1 divided by C. Now, here the C is not given a subscript 1, because whether if you have to take an acid, if at different concentrations you cannot compare their strength. So, the concentration has to be constant, that is concentration should be C itself, it should not change. And in this case alpha 2 will be equal to square root of Ka 2 by C, same concentration. Now, I am going to compare that alpha 1 by alpha 2 is equal to square root of, that is Ka 1 by C, that is the first case, divided by, so that comes in the denominator Ka 2 divided by C goes to the numerator. So, C and C get cancelled and the value will be alpha 1 by alpha 2 is equal to square root of Ka 1 by Ka 2. So, this gives us a relationship between like the how much the acids has been dissociated. We get an idea about that, which dissociates more or the which one dissociate less, or you can say it is a comparison, or it is a comparison, or you can say it is a relative strength of the two acids. Next, what we are going to see is for a weak base. This is for a weak acid. Alpha was given as square root of Ka by C in the case of a weak acid. Now, let us see what will be the value of alpha when it is in terms of a base. Again, I am taking a weak base. This is a weak base which is represented as BOH, which ionizes to give B plus and OH minus ions. Initial concentration, just like the above case, it is C moles per liter and you have 0 moles at the initial stage, and at equilibrium again if I consider alpha as the dissociation constant or ionization constant, we get C into 1 minus alpha, the other two will be C alpha and C alpha, same explanation which I had given for the acid itself. Okay. Now, I am going to take the equilibrium constant Kb. Kb is equal to the product of molar concentration of B plus into molar concentration of OH minus. So, these are the product of these two molar concentrations. They are the products divided by that of the reactants, that is BOH. So, that will be Kb. Now, I am going to put the concentrations here. Concentration of B plus is C alpha into C alpha whole divided by C into 1 minus alpha. Here one C gets cancelled and the value becomes C alpha square by 1 minus alpha. This is the same expression which we got for Ka. In this it is Kb and the other case it was Ka. Now, again we are going for the approximation. So, alpha is small. You can approximate 1 minus alpha equals 1. So, the expression takes the form Kb is equal to C into alpha square, because 1 minus alpha in the denominator turns to be 1. Now, alpha, the degree of dissociation, is equal to square root of Kb by C. In the case of acid, it was Ka by C. In the case of a weak base, it is Kb by C. So, it is very easy to remember and we have to do problems based on these equations and therefore, you have to by heart it. So, alpha is equal to square root of Kb by C. Now, again in this case, you can see when concentration increases, alpha decreases. That means, ionization is greater in dilute solutions. Next, we will see what is pKb, that is Kb, you know, that is you have to take the negative logarithm to the base 10 of Kb instead of K. So, it becomes pKb. The value of Kb, if it is high, the acid is the base is strong. If the value of pK is low, the base is strong. Same with that of the acid too. Now, just like in acid, we are going to compare the relative strength of weak bases, just like as we have done in the acids. So, here we have base 1 and base 2 at the same concentration C. We will have to keep the concentration fixed. Let alpha 1 be that of base 1 and alpha 2 that of base 2. Then we can put alpha 1 is equal to square root of Kb 1 of the first divided by C. Alpha 2 will be equal to square root of Kb divided by Kb 2 divided by C. Okay. Now, for comparison, I am taking the ratio alpha 1 by alpha 2, which is equal to square root of Kb 1 divided by C, which is again divided by Kb 2 divided by C, that goes to the numerator, C and C gets cancelled and final value will be alpha 1 by alpha 2 is equal to square root of Kb 1 divided by Kb 2. So, this gives a value for relative strength of two acids. Just we have to take the ionization constants or ionization values for both acids and you can compare the strength of the acid. Next is dissociation constants for polybasic acid. Polybasic acid means they have more than one hydrogen ion to be replaced. First, I will take a simple one, which is a sulfuric acid. Sulfuric acid in water dissociates to give H3O plus, that is one of the proton is lost, the remaining will be HSO4 minus. Again this HSO4, which is again capable of donating a proton with water, gives H3O plus, again water takes one more proton and finally results in SO4 minus. Now, this ion does not have any hydrogen ions and therefore, there is no further ionization. So, let this be Ka1, that is for the first ionization, and let this be for the second ionization, Ka1 and Ka2. In the case of Ka1, the expression will be concentration of H3O plus multiplied by concentration of HSO4 minus whole divided by concentration of H2SO4, water being present in excess. Ka2, again we have the H3O plus ion same, but here this ion is different. This is the sulphate ion, whole divided by concentration of HSO4 minus. Now, in this case, it has been found that Ka1 will be always greater than Ka2, and for getting the overall Ka value for sulfuric acid, what we do is multiply Ka1 into Ka2. That is the overall dissociation constant for sulfuric acid. So, you take the product of both. Now, why does Ka1 being greater than Ka2? So, the first ionization constant is always greater than the second ionization constant. The reason for that is, in the first case, the H plus ion is given out from a neutral molecule sulfuric acid. Once sulfuric acid loses one proton, it attains a negative charge, and in the second case, the proton has to be eliminated from a species which is already carrying a unit negative charge, which will be difficult. And therefore, in this case, you have to put a double arrow, because there is a tendency the reaction should occur backwards to some extent, and therefore, in this case the value of Ka2 will always be less than the first ionization energy. Now, let us take another acid. Here we had 2, let me take another acid H3PO4, which has got 3 replaceable hydrogen. So, with water again it gives H3O plus, with one of the proton lost, it will be H2PO4 with a single minus charge. Next case, it will be H2PO4 plus water giving H3O plus one more hydrogen is lost. So, that will be HPO4, already it has got one minus sign over here. So, it becomes 2 minus. Next, HPO4 2 minus will react with water giving H3O plus PO4 3 minus. Again, in this case also you will be having Ka1, Ka2 for the second one, and Ka3 for the third ionization. Now, again as in the above case, it has been found that Ka1 is the highest one value, greater than Ka2, which in turn is greater than Ka3. The same explanation applies here, because in the first case the ionization is from a neutral one, the second case it is a uninegative one, the third case it is having 2 negative charges. So, from that dissociation of a proton will be more difficult, and therefore, these values goes on decreasing as the step increases, and the overall Ka value will be obtained by Ka1 into Ka2 into Ka3. That will give you the overall K value for phosphoric acid. This is phosphoric acid H3PO4. It's a tribasic acid. Now, let us go for the problem. Here, calculate the degree of ionization of acetic acid in a solution that is having a concentration of 0.01 molar, given that Ka is equal to 1.8 into 10 to the power minus 5 at 298 Kelvin, and you are supposed to find out the concentration of H3O plus, pH of the solution and Kb of its conjugate base. Now, here we have the acid acetic acid. First of all, what we are going to do is, I am going to write down the ionization of acetic acid. Of course, I will have to put water because it will be ionizing to give a proton. H3O plus, proton donated to water, and remaining you will be having CH3COO minus. Okay. Now, the strength of acetic acid is 0.01 molar. Of course, from acetic acid the same amount of hydronium ion may not be available. It is not sure that whether it will have that much or not. But one thing we can say that this is the initial concentration. Now, here it will have, like we used to write the expression as C into 1 minus alpha, and here that will be C alpha into C alpha, that will be the concentrations. If you get the concentration of H3O plus, you can find out the pH. So, first thing what we have to find out is the concentration of H3O plus. To find the concentration of H3O plus, you should know what is the value of alpha, which they haven't given. Instead, they have given the dissociation constant of the acid. So, using that I can find out the concentration of H3O plus. Now, Ka is equal to 1.8 into 10 to the power minus 5 moles per liter. Now, we know the expression for a weak acid, alpha is equal to square root of Ka by C. Ka is given 1.8 into 10 to the power minus 5 whole divided by the concentration 0.01, and the answer, if you solve it, you will get it as 0.04243. So, we have found out the first value, alpha the degree of dissociation. Next, I have to find out the concentration of H3O plus. Concentration of H3O plus as seen from the equation, that will be equal to C into alpha. Alpha has been found out. C is 0.01 multiplied by 0.04243. That will be equal to you increase 2 zeros, 4243 will be the so much moles per liter. That will be the answer. So, we got the value of H3O plus. Next, we are supposed to find out the pH. How will you find out the pH? Just take the negative logarithm. pH is equal to negative logarithm to the base 10 of H3O plus ion concentration, and that is equal to minus of log to the base 10. What is the concentration? That is equal to 0.304243. Now, how to do it? First press negative sign, press log, and in bracket you give the value. You get the answer as 3.37 0.23, that will be the pH. Next, we have to find out the value of Kb. We know that Ka into Kb will be equal to Kw. Ka into Kb is equal to Kw. That is an expression, that is product of Ka and Kb will be equal to Kw. We know Ka, but we do not know Kb. So, how will you find out Kb? Kb will be equal to Kw by Ka. Kw means it is 10 to the power minus 14 whole divided by Ka. Ka, the value is equal to 1.8 into 10 to the power minus 5, and that will give you the value as, if you calculate it as 5.55, I think it is 5556 into 10 to the power minus 10 moles per liter. So, it is simple, but you have to remember this expression Ka into Kb is equal to Kw, and Kw will be equal to, that is the conjugate base. Conjugate base means that is the Kb value for acetate ion, that is equal to Kw by Ka. K is given, you just divide it, you get the answer as 5.5556. Now, let us conclude this session. Ionization constants of weak acids as well as Ka and pKa we found out. In the similar way, for the bases we found out Kb and pKb. All these are utilized to find out the relative strength of the acids or bases, whichever is needed. Then we found out the dissociation constants for polybasic acids. In polybasic acids, the problem is once one of the proton is ionized from that, it becomes negatively charged species, and for the second ionization it will be difficult because hydrogen ion has to be departed from a negatively charged species. For the third, it will be di-negative species from which the hydrogen ion is departed. In these cases, you can see that first ionization energy will be the highest, second, third and the following ones will be lower, it goes on decreasing. And actually for a acid we say the overall one, which is the product of all these ionization constants. Thank you.